Hello viewers, today I'm going to give you lectures on the main tools needed for problem solving in the mole concept. Now, to know these tools, you should meticulously watch this video from the start to the end to understand those tools that you need to handle nightmare questions on the topic the mole concept. I will be back in a minute. To start with, what is the mole concept? And why do you study the mole concept? The mole concept is an imagination that enables scientists to compute or count the number of particles present in a substance without the use of any complicated or sophisticated machine. The number of entities, also called the number of particles, present in a solid is determined by weighing the solid to know its mass, whereas the number of particles present in a liquid or gas is determined by measuring its volume. The mole concept is very important to count particles without stress, because if we imagine a sophisticated machine that is able to count 1 billion particles every second, then it will take 1.91 times 10 to the power 7 years, or approximately 20 million years, for it to finish counting 6.02 times 10 to the power 23 particles or entities. Secondly, the mole concept is very important because an atom is very small, with its diameter ranging from 0.1 to 0.5 nanometer, which may not be seen with a light microscope. Remember that 1 nanometer is equal to 1 times 10 to the power minus 9 meter, or 1 billionth of a meter. Dear viewers, whenever you come across a problem in mole concept, ask yourself this simple question: what state of matter am I working with? It's funny, if I ask you to know the state of matter before embarking on problem solving in mole concept, right? That shouldn't perturb you. However, matter exists in 3 physical states: solid, liquid, and gas. Therefore, problem solving in mole concept must be governed by 3 physical laws or equations, since the mole concept is part of physical chemistry. For solids, the number of moles is given by given mass divided by molar mass, or given mass divided by relative molecular mass, or given mass divided by relative atomic mass. For liquids or aqueous solutions, the number of moles is given by molarity times volume. And for gases, the number of moles is given by volume of the gas divided by the molar volume. During these lectures, I will discuss on the following 7 subtopics. 1.1 Relative atomic mass. 1.2 Empirical formula of simple organic compounds. 1.3 Molar constants and molar quantities. 1.4 Gas laws. 1.5 Concentrations of homogeneous solutions in mole per cubic decimeter and mass concentration in grams per cubic decimeter. 1.6 Titrations and 1.7 Calculations involving limiting reagents. Let's start with 1.1 The relative atomic mass, denoted uppercase A, lowercase r, or simply RAM in uppercase letters. The relative atomic mass is defined as the number of times the weighted average of the naturally occurring isotopes of an element is heavier than 1/12 the mass of a carbon-12 atom, or the relative atomic mass equals the average mass of all the atoms in an element compared or relative to 1/12 the mass of a carbon-12 atom. The relative atomic mass of each element equals 1 mole. The mole of a substance, denoted lowercase n, is defined as the amount of that substance that contains the same number of elementary particles as there are atoms of carbon in exactly 12 grams of carbon-12 isotope. Examples of these elementary particles are atoms, ions, molecules, electrons, protons, etc. The base symbol for the mole is MOL, all in lower case letters. 1 mole of any substance contains a constant number of particles, which is 6.02 times 10 to the power 23, and is called the Avogadro's constant. By definition, the Avogadro's constant, denoted uppercase L, is defined as the number of entities in 1 mole of any substance. Therefore, another definition for the mole of a substance is the amount of substance that contains the Avogadro's number of particles. Experiments have shown that 1 mole of any substance, or 12 grams of carbon-12, contains 6.02 times 10 to the power 23 particles. The number of particles, denoted by lowercase x, is related to the mole and Avogadro's constant by the equation x equal to NL. 1 mole of a substance can be expressed in grams, and this refers to the molar mass. Therefore, the molar mass of a substance, denoted uppercase M, is the mass of 1 mole of that substance expressed in grams. Its unit is grams per mole. It is the relative molecular mass or formula mass expressed in grams. By definition, the relative molecular mass of a substance, that is, molecule of an element or compound, denoted uppercase M, lowercase r, or simply RMM, all in uppercase letters, is the number of times the average mass of one molecule of it is heavier than 1/12 the mass of one atom of carbon-12 isotope. Practically, it is a sum of all the relative atomic masses in one molecule of a substance. Unlike relative molecular mass, the formula mass refers not only to a molecule, but also to ions and radicals. We can meticulously select a formula for calculating the number of moles of a solid whose mass is known from the following relationship. Number of moles equal to giving mass over relative atomic mass equal to giving mass over molar mass equal to giving mass over relative molecular mass. Before we move to the second subtopic, take this nota bene. In part 2 of mole concept, which will be coming up in the next video on this topic, based on calculations only, I will be using uppercase M lowercase r to stand for molar mass and relative molecular mass, and uppercase M for molarity. I will be doing this intentionally to avoid confusion between molar mass and molarity. Now, let's look at subtopic 2, empirical formula of simple organic compounds. The empirical formula is defined as the simplest formula of a compound which gives the simplest whole number ratio of atoms of each element present in a compound. In some cases, especially in organic chemistry, the empirical formula provides a clue to determine the molecular formula. The molecular formula is defined as the formula of the compound which gives the exact number of atoms of each element present in one molecule of the compound. The amount in terms of mass of each element in a substance is defined by its percentage composition. The percentage composition is defined as the percentage by mass of each element in a compound. The percentage composition of an element in a compound is calculated with the help of the following equation. Now let's look at subtopic 1.3, molar constants and molar quantities. The very first one that we are going to consider here is the Boltzmann's constant, denoted lowercase k. The Boltzmann's constant is defined as the ratio of the universal gas constant to Avogadro's number and is equal to 1.38 times 10 to the power minus 23 joules per Kelvin. Mathematically, we can write K equal to capital R over capital L, where R is the universal gas constant, also called molar gas constant. numerically equal to 8.314 joules per Kelvin per mole. And L is the Avogadro's constant, numerically equal to 6.03 times 10 to the power 23 entities per mole. The pressure P of an ideal gas is related to the Boltzmann's constant by the equation P equal to uppercase N KT, where uppercase N is the number of gas molecules per unit volume and T is the temperature of the gas. Uppercase N is equal to lowercase n times L divided by V. Therefore, P equal to lowercase n times L times K times T divided by V. And rearranging this gives the ideal gas equation, which is PV equal to nRT. Now let's take a closer look at Faraday's constant denoted uppercase F. The Faraday constant is defined as the amount of electric charge carried by 1 mole or Avogadro's number of electrons. It is an important constant in chemistry, physics, and electronics. It is expressed in coulombs per mole. The value of Faraday constant is approximately 96,500 coulombs per mole. One of the most common uses of Faraday's constant is in electrolysis. Dividing the quantity of charge in coulombs by Faraday constant gives the amount in moles of elements that have been oxidized. The formula to calculate Faraday constant is uppercase F equal to lowercase e uppercase L, where E is the charge of electrons in coulombs, numerically equal to 1.6 times 10 to the power minus 19 coulombs, and L is the Avogadro's constant. Now, I will discuss on the molar quantity, molar gas volume, denoted uppercase V, lowercase m, that is Vm. The molar gas volume Vm is the volume occupied by 1 mole of any gas at a given temperature and pressure. The number of moles N of any volume of a gas, that is V of the gas, is related to the molar volume Vm by the formula lowercase n equal to V gas over Vm. The value of the molar gas volume depends on the constant temperature and pressure under which the gas is subjected. At constant temperature and pressure, STP, i.e. 273 K or 0 degrees Celsius and 1 atmosphere, the molar gas volume is 22.4 cubic decimeters or 22,400 cubic centimeters. At room temperature and pressure, that is RTP, we have 298 K or 25 degrees Celsius and 1 atmosphere. Under this condition, the molar gas volume is 24,000 1000 cubic centimeters or 24 cubic decimeters. Finally, the molar heat capacity denoted uppercase C, lowercase n as the quantity of heat needed to raise the temperature of 1 mole of a substance by 1 Kelvin. Its SI unit is joule per mole per Kelvin. Therefore, molar heat capacity is specific heat capacity per unit mass. The value of molar heat capacity differs from one substance to another. Molar heat capacity of a substance, Cn, is related to the quantity of heat, Q, induced, the number of moles, lowercase n, and the temperature change, delta T, by the equation Cn is equal to capital Q divided by the product of mole and change in temperature. The fourth subtopic on our list is gas laws. Let's begin with Boyle's law. Boyle's law states that provided the temperature is kept constant, the volume of a fixed mass of gas is inversely proportional to its pressure. Mathematically, V varies with 1 over P. This means that PV equal to K, where K is a constant of proportionality when temperature is kept constant. P is the pressure of the gas and V its volume. Next, let's consider Charles' law, which states that provided the pressure is kept constant, the volume of a fixed mass of gas is directly proportional to its absolute temperature. Mathematically, we write V varies directly with T. This means that V divided by T equal to K, where K is a constant of proportionality when pressure P is kept constant. V is the volume of the gas and T is its absolute temperature, also known as the Kelvin temperature. Thirdly, let's take a closer look at Gay-Lussac's law. Gay-Lussac's law is also known as a pressure law. Gay-Lussac's law states that provided the volume is kept constant, the pressure of a fixed mass of gas is directly proportional to its absolute temperature. Mathematically, P varies directly with T. This means that P divided by T is equal to a constant, where K is a constant of proportionality when volume V is kept constant. P is the pressure of the gas and T is its absolute temperature, also called Kelvin temperature, as I said earlier. Now, the last but not least, the combined or ideal gas law. A combination of Boyle's, Charles' and Gay-Lussac's laws gives the following equation: PV divided by T equal to K, where K is a molar gas constant, uppercase R, whose value is 8.314 joules per Kelvin per mole. Therefore, PV divided by T equal to uppercase R, the molar gas constant. The latter equation is consistent with 1 mole of gas. However, for n moles of gas, the ideal gas equation is obtained. Mathematically, PV divided by T equal to nR, or PV equal to nRT. The equation we have just written is the ideal gas equation. Nota bene. Great care about the units should be taken when using the ideal gas equation. When R equal to 8.314 joules per Kelvin per mole, the volume V and the pressure P must be expressed in cubic meters and pascals or Newton per meters square respectively. When R equal to 0.082 dm cube atmosphere per Kelvin per mole, then the volume V and the pressure P must be expressed in cubic decimeters and atmospheres respectively. R has been calculated using conditions of STP. Use your calculator to check it. Use Kelvin temperature when you are solving problems on gas laws. Now, subtopic 1.5, concentrations of homogeneous solutions in moles per cubic decimeter and mass concentration in grams per cubic decimeter. Let's consider some definitions. Very first one is concentration, which is defined as a quantity or amount of solid in a given volume of solution or solvent. Next, a standard solution is a solution whose concentration is known precisely. Thirdly, a primary standard is defined as a reagent that is extremely pure, stable, contains no water of hydration, and is of high molecular weight. Examples of primary standards are sodium carbonate for the titration of acids, potassium hydrogen iodate for the titration of bases, and potassium dichromate for redox titrations. Finally, a secondary standard is defined as a standard that is prepared in the laboratory for a specific analysis. It is usually standardized against a primary standard. Examples are sodium hydroxide, potassium hydroxide, hydrochloric acid, sodium thiosulfate, and potassium permanganate. Dear viewers, two parameters, or simply units, are used to express concentration of solutions at ordinary and advanced level. They are molarity and mass concentration. 1. Molarity, denoted uppercase M. Molarity is defined as the number of moles of solid divided by the number of cubic decimeters of solution. Molarity is one of the units of expressing the concentration of a solution and is equal to moles per cubic decimeters. Examples: a 1 Molar solution is a solution which contains 1 mole of solute in 1 liter of it. A 2-molar solution is a solution which contains 2 moles of solute in 1 liter of it, etc. Mathematically, uppercase M equal to N divided by V, where N is a number of moles and V is a volume in cubic decimeters. Nota bene, 1 cubic decimeter equal to 1 liter equal to 1000 milliliter, which is equivalent to 1000 cubic centimeters. 2. Mass concentration denoted uppercase M lowercase c. The mass concentration is defined as the mass of solute divided by the number of cubic decimeters or liters of solution. Just like molarity, mass concentration is one of the units of expressing the concentration of a solution and is equal to grams per cubic decimeter. A 1 gram per cubic decimeter solution is a solution which contains 1 gram of solute in 1 liter of it. Similarly, a 2 gram per cubic decimeter solution is a solution which contains 2 grams of solute in 1 liter of it, etc. Mathematically, mass concentration equal to M over V, where M is the mass in grams of a solute found in a solution of volume Vm cube. Mass concentration is connected to molarity and molar mass or relative atomic mass by the formula MC equal to M times Mr, or MC equal to M times AR. Nota bene, 1 kilogram equal to 1000 grams, which is equivalent to 1 million milligram. Subtopic 1.6 Titrations. A titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. There are 4 major types of titration. Acid-base titrations, in which an acid or base titrant reacts with a titrant or analyte that is a base or an acid. Complexometric titrations based on metal-ligand complexation. Redox titrations, in which the titrant is an oxidizing or reducing agent. And precipitation titrations, in which the titrant and titrant form a precipitate. Some titrations involve back titration. A back titration or indirect titration is a titration method where the concentration of an analyte is determined by reacting it with a known amount of excess reagent. The remaining excess reagent is then titrated with another second reagent. Interpretation of chemical equations is very important in titration experiments, where the concentration of the analyte, that is a solution of unknown concentration, is determined using another solution called titrant, that is a solution of known concentration. To determine the concentration of the unknown in a titration experiment involves the use of mole ratio. Hence, a balanced chemical equation is indispensable in solving problems associated with titration experiments. Consider the reaction between sulfuric acid and sodium hydroxide. A balanced chemical equation for this reaction is The expression for mole ratio is where Na and Nb are the stoichiometric coefficients of sulfuric acid and sodium hydroxide respectively. Ma and Mb are the molarities of sulfuric acid and sodium hydroxide respectively. Va and Vb are the volumes of sulfuric acid and sodium hydroxide respectively. In general, for any type of titration, the mole ratio is written as nota bene. We have taken ratio of the theoretical moles on the left-hand side, then equated it to practical or experimental ratio on the right-hand side. In other words, we have related theory to practical. You know, this is awesome. After a titration experiment, you must write a balanced chemical equation, then write the mole ratio equation, and finally solve for the unknown concentration or molarity. Predict what will happen if the chemical equation is not balanced. After this interesting nota bene, let's understand what the percentage yield is all about. The percentage yield is defined as the percent ratio of the actual yield to the theoretical yield. The actual yield or experimental yield is the quantity of a product that is obtained from a chemical reaction. The theoretical yield is the amount of a product predicted by the chemical equation, or it is the amount of product that could be obtained from a chemical reaction if all the reactant, usually limiting reactant or reagent, is converted to product. The theoretical yield is therefore based on the limiting reactant. It is impossible to attain 100% yield in a chemical reaction because of the following reasons. Some of the product may be lost when it is separated from the reaction mixture. Some of the reactants may react in different ways to the expected reaction, making it impossible to get the entire expected or predicted product. Reversible reaction may not go to completion. Errors may be made during weighing of reactants and products. Percentage yield equal to actual yield divided by theoretical yield multiplied by 100. Therefore, it is important for us to understand what limiting reagents are in order to solve some problems in mole concept, namely percentage yield, the amount of product in terms of mass, and number of moles. The last but not least, subtopic 7. Calculations involving limiting reagents. A limiting reagent is defined as a reactant in a chemical reaction that determines the amount of product that is formed. 4. chemical reactions involving more than one reactant, once one of the reactants gets exhausted, the reaction stops abruptly. Such a reactant is termed a limiting reagent for that reaction. The excess reagent is a reactant that is left over after the reaction stops because the limiting reagent is all used up. How do you know that this reagent or that reagent is a limiting reagent? I will answer this question in one of my videos on the mole concept, part 2, problem solving only. Thanks for your keen attention. Thanks for watching.